Hello calculus students and general seekers of the truth, and welcome to the video on finding the volume of solids of revolution. So before we really begin into this example and a few other examples, I'm going to let you know that you need to watch the prerequisite video on solids of revolution. If you haven't seen these videos already, please stop now and go watch those ones. Look in the description of this YouTube video for a link, because we're going to get into some technical details here, and if you don't understand the general idea, the technical details will be quite confusing. So if you have not, please do so now. Watch and make sure you understand the big picture. All right, so moving on, we have this question that says, find the volume of the solid formed by rotating y equals e to the x around the x-axis. Okay, so let me draw a picture of what this object is going to look like. So this is the graph of y equals e to the x. I should point out here that this point here is 0, 1. Oh, and I forgot to write this in. It should be bounded between x equals 0 and x equals 2. Okay. So basically, what we're going to do is take this curve and spin it around this axis right here, around the x-axis, and I'm going to try to render this picture as best I can. Okay, so it's going to look like this, and we're going to cut it off at x equals 2. Okay, because if we don't cut that off, this volume is you're gonna have a volume that is infinite. Okay. Let me draw this a little bit. Maybe fix this graph here, make it look a little bit more symmetric to what's going on the top there. Okay, so we're interested in this section right here. Now, the 3D version of this is essentially a bunch of circles, right? So this is kind of a circular. This is going to be like a cone with parts of it, with the top and the bottom cut off a little bit. So we're looking for the volume of this object in here. Okay. Now, if you notice that the volume of this object is essentially a series of infinite circles. Okay, so if we just take an infinite number of circles and add up all of their areas, then we essentially have this object. Okay, so this is why it's called the disk method, because what you really have here is you got that disk, and then you have a slightly bigger disk, and a slightly bigger disk, and a slightly bigger disk. And if you haven't, and then you just add up the area of an infinite number of these disks. Okay. So that's the big idea here, is add areas of infinitely many disks, or in this case, they're circles. Okay, in this case, these are going to be circles. So around here all the way. I've drawn them as ellipses. They look like ellipses because I'm trying to render a 3D picture onto a two-dimensional surface, so it looks like an ellipse. But if we were to look at the 3D rendering of it in the videos, and you'll see that these would actually be circles. Okay. All right. So the way that we handle infinitely many is that we're going to take the integral. So we're going to take the integral of some expression that gives us all of these areas, or the areas of all of these circles. So the area of a circle formula is pi r squared. However, one very important note here is that r changes for each of these circles. Okay? R is actually a variable, because the circle that's at the short end here has a smaller radius than the circle that has a big end here. Okay? But it's not too difficult to find out, because if you look at this picture, the radius of the circle in this case happens to be the height of this function right here. Okay, so in this case, r is equal to y. Whatever is the value of y at that point in the coordinate plane, that also happens to be the radius of the circle. So, and I notice here, I haven't given the dy or dx yet, because we have to make that decision. In this case, we're going to integrate, we're going to add up the areas of all these circles along the x-axis. So it's going to be dx. And we're going to go from x equals 0 to x equals 2, since that's what we were given as the bounds. So from this point on, it's just a matter of doing some calculations and of course changing the variables so that you change r into x. Now remember, r is the same thing as y, and y is equal to e to the x. So I'm going to pull the pi out to the front here. So all that's left for us to do here is to integrate this, and this is simple enough that we're going to do it by hand. So this is equal to pi integrated between 0 and 2 of e to the 2x dx. So this is going to give us pi times 1/2 e to the 2x evaluated between 0 and 2. If you plug 2 in here, you get, and pi is just going to be the multiplying factor. In fact, pi over 2 is going to be the multiplying factor here. If you plug 2 into here, you get e to the 4th. And if you plug 0 into there, you end up with 1. So e to the 4th minus 1 times pi over 2 is the volume of this object here that we create by revolving e to the x around the x-axis. Okay. So there you have it. Just a quick example that shows how to evaluate the volume of a rotated solid. And the main idea is, of course, that we're just going to add up an infinite number of circles. Hence, this is called the disk method, because we're just stacking a bunch of disks on top of each other, or next to each other in this case, until they form the entire three-dimensional object. Okay. So I'm going to end this video here. We'll continue another one where we talk about rotating around the y-axis.